All right, and now we've got the pleasure of hearing from Robin Deits from MIT.
First, a huge thanks to Bora for rescuing me from a laptop disaster. So fortunately, I have the ability to present slides. So hi, I'm Robin Deits. I'm from the Robot Locomotion Group at MIT, and I want to talk about learning contact-aware controllers. So controllers that can make decisions about contact using global optimization. So the motivation is still the same as it was last year when I was here. We want controllers that don't just fall apart spectacularly when something bad happens. So at the DRC, we fell apart pretty spectacularly when there were unmodeled contacts between the robot and the world. We want the robot to exploit contact, not to be absolutely terrified of it. To do that, we're going to focus on a very simple center of mass model, a little bit more than something like a linear inverted pendulum. Instead, we're going to take something like the Atlas robot, model that as a center of mass with limbs that have mass themselves, and model the contact between those limbs in the world. I'm going to focus everything I'm talking about in a planar system just to keep things simple. I think a lot of these ideas extend to 3D, but we haven't tried it yet. From that simple model, we're going to create a simple humanoid that we can use to control. Okay, so the general approach is still this language of model predictive control, which is a very simple idea, which is if you have no idea what to do about a system, but you can simulate it, well, just simulate it really fast. So every time step, you run a short trajectory optimization, choose the best input from the beginning of that trajectory, apply it, and repeat. This works great if you can actually optimize trajectories at a reasonably high control rate. We definitely can't for this system. I said it works great. Only if you can actually solve these optimizations. So the first step, even before trying to solve them quickly, is to be able to solve these problems at all. There are issues with planning trajectories around contact and for systems whose dynamics are nonlinear. So we're going to model a robot as piecewise linear, including discrete events when it makes contact. And that's going to let us write down a mixed integer convex program. The nice thing about this kind of program is it can be very expensive to solve, but we have a reliable algorithm, which is branch and bound, that can actually solve it to global optimality. Now, one of the nice things about branch and bound, which I'll get to at the very end, is that actually, instead of solving to global optimality, sometimes we can just solve partway and get something reasonable. So a good answer and a good bound on how good any answer could possibly be. That's going to turn out to be useful. So last year, Dynamic Walking in 2017, I presented an idea, which was we're going to run a lot of optimizations offline. We're going to create a big database. We're going to run some machine learning, and we're going to learn a policy. So learn a map from robot state to robot actions for a particular environment. And that worked okay for this really simple like pendulum system where it can make contact with the walls. And then I don't have any video of that working for Atlas because it doesn't. It totally didn't work. Which I think is kind of cool. It's fun to be wrong. So it totally fell apart because the problem is these optimizations, yes, we can solve them to global optimality, but sometimes it could take minutes or hours. And collecting samples in a 20-dimensional state space, if it takes an hour per sample, is just not going to work. I mean, we could throw incredible amounts of computing power at it, but it's just not a good idea. So we need something better. Okay, this year, 3 observations. First, branch and bound gives us rigorous upper and lower bounds on the cost of an optimization, even if you stop early. Observation 2, if you know the cost of a model predictive control optimization, you know the cost to go from a given state. And 3, if you know the cost to go of a robot, you actually know how to control it, because all you have to do is greedily go downhill. Going downhill greedily on the cost to go is the right thing to do. So the idea is we're going to learn the cost to go, learn the value function from partial optimization. We're not going to solve programs all the way to completion. We're just going to solve them a little bit, get some useful bounds on how good this particular state might be, and then move on with our lives. We'll take a collection of those samples and use those to train a function that emulates the cost to go. And so that might look like this. So each of the points with a vertical line between them is a single optimization. The points are far apart when we couldn't solve all the way to optimality. They're close together when we could. And so what we've shown in the green line is a function that's learned to fit somewhere between those points. The red line is the LQR cost to go. So that's a very simple linear model of the system. It agrees well in the origin, so this X scale is how fast the robot is moving. So when you're not moving very fast, LQR is fine. When you are moving fast, it's completely wrong. But the green curve is a much better fit for the actual data. Okay, but that's all just graphs. It's better with videos. So on the left I have, on your left I have the LQR controller, so a very simple linear controller. And on the right I have the controller that's using that learned cost to go. So this controller isn't solving optimizations online, at least not big ones. It's not quite as fast as real time, but it's getting very close. And so as we decrease the size of the perturbation, the neural net keeps doing well. LQR does very badly. So the learned cost to go is doing well. For very small perturbations, linear controllers are fine. but I still think our learned cost to go works better. And as we push the robot in the other direction, it's actually even able to use things like putting the hand out to touch the wall, so exploiting additional contacts with the world. Okay, so to conclude, we can learn a lot from these global optimizations even when we don't solve them to global optimality. We can use that information to make cool contact-aware controllers. Now, all of the work that I've shown is specific to a single environment. If you ask me how to take a controller that works on a floor and a wall and apply that to a table, I don't know yet. Maybe next year I will. And the remaining big open question, though, is I've shown you some things that work on simple models. How do we apply this to the full Atlas robot? And yeah, check with me next year. Finally, I should say that this is all done in Julia, so come to our Julia robotics talk on Friday and you'll learn how to be cool, just like us. Thanks, guys.
Thanks, Robin. Yeah, Neil, go ahead and get set up because we're over time. I'm going to be selfish and ask, go ahead and unplug the computer. I'm going to be selfish and go ahead and ask the connection between the previous talk, my student's talk, and your talk. What happens if your value function landscape, the actual value function landscape, is riddled with discontinuities?
Yeah, so the network structure that I'm using is continuous. So we can't sorry, that was dumb. We can't accurately reproduce a discontinuous function. We can hope that A, it's not too discontinuous, or that we will learn a sufficiently steep response in between the discontinuities. Yeah, I've spent some time thinking about whether it makes any sense to try to learn a discontinuous function with a continuous approximator. The problem is I don't know how to train a discontinuous approximator, but I would love to know how to do that.
It's an interesting question. Thanks very much, Robin. Next up, we have the pleasure of hearing, oh yeah, please.